All right, hello Math 282 students. So this was an example we worked on last Thursday in class, where we had a differential equation, first order differential equation, where the function f of t is a piecewise function. Okay, this piecewise function here. So the driving force is a piecewise function. And normally, to solve a differential equation, a non-homogeneous differential equation where the right-hand side is a piecewise function, it's a little bit of a nuisance using the techniques you've learned. Well, Laplace transforms provide a nice way to solve for that. So what we have to do is we have to write this piecewise function f of t as in terms of the unit step function, and we did that. So in the solution, that piecewise function f of t was equal to 3 times the cosine of t times the unit step function at t minus pi. Okay, so we did that, and then we took the Laplace transforms of both sides of the differential equation, and now of course, the Laplace transform of y prime, well, that's the Laplace transform of a derivative. So that would be s times the Laplace transform of y minus the y at t equals 0. And remember, the Laplace transform of y prime we denote by big function y of s. Okay, y is a natural variable to use because we're doing y prime. We're trying to solve for y. So we talked about then, writing the right-hand side as you see here, because that allows us then to use the second translation theorem to take the Laplace transform of the right side, and then. As usual, we want to get on the left the Laplace transform by itself, so we divide by s plus 1. Okay, and we then what we did was we recognized that s over s plus 1 times s squared plus 1, we recognize that that's a fraction. We have to write that out. We have to expand that out. And so we did a partial fraction expansion. Okay, we did a partial fraction expansion, and when we did that, we determined that a was equal to negative a half, b was equal to a half, and c was equal to 1/2. And so we substitute those back in for a, b, and c here. Okay, and so therefore, this rational function will equal negative 1/2 over s plus 1 plus 1/2 s plus a half over s squared plus 1. Okay, that's what it'll equal. And now we substitute that back in the differential equation, and that gets us here. And then I'm going to factor a 1/2 out from the right-hand side, which will give me this negative 3/2 here. And then what I want to do is I want to take this fraction here and expand it out like I do here. So what we're going to be doing we have here on the left-hand side the Laplace transform of y of t, right? And we're going to have to take inverse Laplace transforms of both sides in order to solve for y of t. But before I do that, I got to prepare the right-hand side of the differential equation to do that. And so that's what I've done here. The right-hand side now of the differential equation is prepared. And so we're going to take inverse Laplace transforms of there are going to be 4 terms here, right? There are going to be 4 terms on the right-hand side. So when we do that, let me just find the right page here. Yeah, when we do that, this is what we get. See, I'm taking the inverse Laplace transform of 1, 2, 3, 4 terms. And of course, we have to use our second translation theorem. Let's see here. Yeah, I mean, and that's what we did. We used it 3 times here. And then I rewrite like the cosine of 1 times t minus pi. That's the same as negative cosine of t. And the sine of 1 times t minus pi is equal to negative sine of t. Okay, and so then we get the following expressions for y of t. Finally, of course, y of t is equal to this function of t here, right here. But you do have these unit step functions. And remember, the unit step functions have t minus pi. Those unit step functions will equal 0 when t is greater than or equal 0 and less than pi. And the unit step functions will equal 1 when t is greater than pi. And so this allows us then to express our final answer, okay, for our solution as this piecewise function. And we know the solution has to be a piecewise function because the driving force changes at t equals pi. Okay, so that's our solution to our differential equation, and I hope this was helpful. Okay, I'll see you in class.